What's up, my dudes? Welcome back to our virtual classroom, where today we're really beating this horse to death. We've done multi-step equations part 1. We've done multi-step equations part 2. Let's make it a three-peat. Let's hit them with the three mix. Let's talk about multi-step equations part 3. So the title of our notes today, however you choose to title them, Unit 1, Class 3. Let's talk about multi-step equations part 3. Now listen, I promise there's a method to the madness here. I am not just trying to cause you pain and suffering for the sake of causing you pain and suffering as much joy as it brings me. That's not what we're trying to do, although it is a nice bonus for me. Remember, last time we said that our goal was to be able to solve any linear equation no matter what it looks like. And the thing is, it can look like a lot of different things. So we're here because we want to expose ourselves to as many different forms of those equations as we can. And the form we're going to talk about today isn't radically different from what we've seen before, but it's different enough that I think it merits a video all its own. So remember, I want to solve equations. That's usually what I'm here to do. When I want to solve an equation, what do I do to solve it? Remind me, we already know what an equation, like solving an equation means, but what do I do in the process of finding that value of the variable that makes the equation true? What do I do? What's my game plan? What's my strategy? 10 seconds? What do you think? Well, to solve an equation, we should know really well. The goal is to make it true. The way that we achieve that goal is by isolating the variable. So to solve an equation, my strategy is to isolate the variable. And if I want to be really explicit, what I mean by that is that my end goal at the end of the day is to have the variable by itself on one side of the equation. So I want something like x equals something, y equals something, k equals something, the variable on one side and ideally some number on the other. So with that goal in mind, I want a copy of the variable on one side by itself of the equation. So then perhaps a natural extension of that question becomes, well, what happens when we encounter an equation with variables on both sides of the equal sign? So take a look at this, friend. I've got 5r minus 2 equals 16 plus 3r. Now, as a mathematician, again, your superpower lies in the ability to ask questions. So a natural question to always ask whenever you see something new is what's different, right? How is something like this different from what you've seen before? Now, I've already kind of given it away here. There's a variable, in this case an r, on either side of the equal sign. So then, if I already know what's different, the question then becomes, well, how do I respond to that difference? I know what I want. I want a variable on one side of the equation. So how, as a mathematician, can I make this problem look the way I want it to look? What choice could I make here to rearrange this equation in some way to make it so that all of my variables live on the same side of that equal sign? Let's game plan. Take 30 seconds, come up with a potential strategy. What could I do to make this look the way I want it to look? And go. And we're back. So 5r minus 2 equals 16 plus 3r. Again, my strategy here is what I'm trying to figure out, but my goal is to get all of my variables on one side of the equation. So, if I have 5r minus 2 equals 16 plus 3r, well, the idea behind the way that this works, say that I wanted to move this negative 2 here over to the right side of the equation. Well, if I wanted to do that, what choice could I make? Take 5 seconds. What choice could I make to move this negative 2 over to the other side? Well, shout it out. What can I do? I can add 2 to both sides. Whoa! Don't shout it out that loud. I could hear you all the way from here. Yeah, I can add 2 to both sides to undo a negative 2. So let's add 2 to both sides here. And in this case, I should know what happens. My inverse operations, these friends undo each other. I'm left with 5r on the left, and then 16 plus 2 is 18, plus that 3r on the right. So, the idea here is that using inverse operations, right, I can add, subtract, divide, multiply by some number on both sides of my equation and still maintain the balance. So the idea is if, for something like this, we can add or subtract a number from both sides, or to both sides, well, a variable, at the end of the day, isn't that just a number we don't know yet? So if I can add and subtract a number from both sides of an equation, well, what's stopping me from doing the same with a variable? So we should, in principle, in theory, be able to do the same with a variable. So take 5r equals 18 plus 3r. The idea is that I want to move all of my variables to one side of the equation. Put your mathematical thinking cap on. What choice could I make here? If I want to get all of these r's over to one side, what choice could I make to achieve that goal? Take 10 seconds. What do you think? Alrighty. Well, if you're like me, I see a 5r on one side and a 3r on the other side. The 18's already on the right, so maybe I want to move my variables over to the left, which means I want to get rid of this positive 3r. Well, inverse operations would tell me if I want to get rid of a positive 3r, a negative 3r should do the trick. So let me subtract 3r from both sides of the equation. Well, look here, I have a positive and a negative 3r. Inverse operations tell me that these two should undo each other. They'll cancel each other out, and I'm left with just an 18 on the right. And then on the left, I've got 5r minus 3r. Well, those are like terms, which means they can be combined. 5r, I take 3 r's away from that. How many r's am I left with? Well, I've got 2 r's left. And from here, would you look at that? I'm in territory that I've already tread. I know what to do. I want 2r equals 18 to become r equals something. The thing standing in the way of that is that 2. The way that I can get rid of it is using my inverse operations. The opposite of multiplication by 2 is division by 2. So let's cancel out our 2's by dividing both sides by 2. It turns out that r is just equal to 18 over 2, which reduces to 9. Fantastic. So with this strategy, we've found a value of the variable that if I were to plug it back in, should make this equation true. I mean, real quick, let's check. So I've got 5r. So if I want to check my work, remember that I can always do that using substitution. So I just need to figure out, is 5, replace my r with a 9 in parentheses, minus 2, equal to 16 plus 3 with a 9 in parentheses. So I'll give myself a question mark because I'm not quite sure yet. Well, 5 parentheses 9 means 5 times 9, which is 45. And then I carry down my minus 2. This is 16 plus 3 times 9 is 27. 45 minus 2, well, that's 43. 16 plus 27, well, 6 plus 7, that is 13, carry my 1, and then 1 plus 1 plus 2 is 43. It works, which means that our strategy, the conjecture that we've made, we've just validated. I can add and subtract variables from both sides in the same way that I can add and subtract numbers. Cool. So let's do a little bit more practice just to make sure that this is really set in. If I scroll down, one that's a little bit different here, maybe a little bit more to work with, 4y minus 11 plus 2y equals 3y minus 17. Again, my goal here is to solve for y, which means I want to get y by itself on one side of the equation. Give yourself a little bit of time. How could I make a series of choices here to get to a place where y is all by itself? Go ahead, take some time, and then we'll chat. Okay, here we are. 4y minus 11 plus 2y equals 3y minus 17. Let's get y by itself. So the first thing that you might notice here, 4y and 2y on the left side, those are like terms. So like we've talked about, sometimes it makes sense to simplify before we solve. I'd say this is probably one of those good cases. I have a 4y and I'm adding 2y. Well, if I combine my like terms, that gives me a 6y. Carry down my minus 11 here, 3y minus 17. So it doesn't really matter which side I get my variable on. Maybe I want to move it to the left. So if I want to get rid of all of the y's on the right, again, what choice should I make here to get rid of a positive 3y? Well, in this case, to undo a positive 3y, let's use a negative 3y. So I'll subtract 3y from both sides. 3y minus 3y is 0. Those guys go away. So I've just got the negative 17 left over. And then on the left side, 6y minus 3y, well, that's 3y's. I still have a negative 11. And from here, I should feel real good about what to do. 3y minus 11, I need to get y by itself. Well, my reverse, ooh, good words, Mr. Volel. My reverse order of operations tell me, well, let's get rid of the subtraction by 11 first. Our SADMEP, let's cancel out our addition subtraction first. 3y is equal to negative 17 plus 11, which, feel free to fact check me, I believe is negative 6. And then if I divide both sides by 3, I'll isolate my y. 3 and 3 undo each other here, and y equals negative 2. Okay, let's take a little bit of time and do one more example together. Now, you can ask yourself that real cool question of, well, how is this one a little different from the ones we've seen before? So take 10 seconds. How is this problem slightly different from the versions that have come before it? What do you think? Are you done thinking yet? I'm done thinking. So in this case, I look at this and I see the difference appears to be in these parentheses. So I've got parentheses. And again, my goal is to get all of my m's here over to one side of the equation. I can't combine my m's until those parentheses disappear. Well, what choice do I have to get rid of parentheses? There's a really nice skill that we've been using all of this year so far that lets me get rid of my parentheses. What is it? What is it? What can I do? Well, if I want to get rid of parentheses, often I want to take the thing right outside it and distribute it to each of the terms inside of those parentheses. So I'll use my distributive property to turn negative 2 parentheses m minus 4 into, well, it's negative 2 times m, and then negative 2 times negative 4, which becomes positive 8, equals 24 minus 6m. Cool. From here, we should feel kind of okay. If you haven't already, give yourself a minute. Let's solve this guy. Negative 2m plus 8 equals 24 minus 6m. Give me a value of m that makes this equation true. And go. And stop. Negative 2m plus 8 equals 24 minus 6m. So here, again, my goal is to get all of my m's over to one side. For the sake of practice, let's try and move them over to the right. So here I want to get rid of all the m's on the left. Well, I see a negative 2m. To undo negative 2m, I should probably use a positive 2m. So I'll add 2m to both sides. On the left, Negative 2m and positive 2m becomes 0. So 8 is left over. I have 24. I have a negative 6m. I'm adding 2 m's to that. So negative 6 plus 2 would give me a total of negative 4 m's. And from here, I want to get m by itself. Reverse order of operations, let's get rid of that 24 first. So I'll cancel out my 24s on the right. 8 minus 24 on the left is negative 16. And if negative 16 is negative 4m, to find the value of m, let's get rid of this negative 4. The opposite of multiplication is division. So we'll divide both sides by negative 4. And m should be equal to positive 4. Fantastic. So with this out of the way, let's do a little more practice. So on your own, you've got 2 more examples here. 2z minus parentheses 1 minus z equals 11 minus z. 8 minus parentheses k minus 4 equals 3 times parentheses 2k plus 5 minus k. So give yourself a little bit of time. Let's see how far we get. Solve for z, solve for k. Let's find the values of these variables that will solve our equations. Give yourself a 3-minute timer this time. Again, don't need to get all the way through, but take a risk, take a chance, see how far you get, and let's come back once we feel like we've made some progress. Alrighty, so 2z minus parentheses 1 minus z equals 11 minus z. So my strategy here, once again, I want to get all of my z's onto one side of the equation. Ideally, I want to also get all of my z's just generally because sleeping is good for me. But here I just want to get them on one side of the equation. Usually I want 3 z's if I'm sleeping, but now I just want 1. 2z minus parentheses 1 minus z. If you're like me, you see these parentheses and you say, I don't like them, I want them gone. Nothing against parentheses, of course, but they keep me from putting my z's together. So here, remember that I can always use the distributive property. In this case, the thing that I'm distributing, there's an invisible 1 here. So it's a negative 1 that I'm taking and giving to each of my terms. So this will become 2z. I distribute a negative 1 to the 1, so that's going to become negative 1 times 1, which is negative 1. And then a negative 1 times a negative z, well, negative times negative, that's positive z. And on the right side, well, I'm just equal to 11 minus z. I'm happy. So 2z minus 1 plus z equals 11 minus z. And from here, I'm in familiar territory. I've got some like terms on the left I can combine. 2z plus z, well, I have an invisible 1 in front, so I have a 2z. I add another z, I've got 3 z's in total. So 3z minus 1 should be equal to 11 minus z. From here, maybe I want to move everything over to one side. Let's choose to get the variables on the left. So the easiest thing to do here to get rid of a negative z on the right, well, what that would be, let's add z to both sides. When I do that, I have 3z plus z. Well, that's 4 z's in total, minus 1 equals 11. I've got 4z minus 1. I want to get z by itself. Reverse order of operations, SADMEP. We know the drill by this point. Let's take plus 1. We'll give it to both sides of our equation. Our negative 1 and our plus 1 undo each other just as this negative z and this positive z undid each other before. 4z equals 11 plus 1, which is 12. Divide both sides by 4 to get z by itself. Our 4's undo each other, and z is 3. And for our last example of the day, 8 minus parentheses k minus 4 equals 3 times parentheses 2k plus 5 minus k. So here, again, my idea, I've got parentheses, I don't like them, I want them gone. So again, I'm going to take this negative sign, I'll distribute it. But on the right side, I'm also going to take this 3 and distribute it. Now, if you want to do this in 2 separate lines, be my guest. For the sake of saving some space, I'm going to do both distributions in the same line. So what I mean by that, I'll start on the left, right? I've got this 8 here, that carries down. And then I'm distributing my negative sign to the k and the negative 4, which is really the same thing, if you haven't noticed already, as just flipping the signs of both of them. So taking my negative sign, we'll flip the sign of k to make it negative k, flip the sign of negative 4 to make it positive 4. If you don't believe me, think of it as multiplying both of them by negative 1. That should check it for you. And then I've got 3 parentheses 2k plus 5. We'll distribute my 3 here. 3 times 2k, that's 6k. 3 times 5, that's 15. And then I'll bring down my minus k here. And now again, I'm in familiar territory. I've got some like terms I can combine. On the left side, notice I've got an 8 plus 4. Well, that's 12, and then I'll bring down my minus k. On the right, I've got a 6k and a minus k. Well, 6k minus k, that's 5k, and then I'll bring down my plus 15. And from here, I'm home free. I've seen this before. I just need to get my k's onto one side and my numbers onto the other. Well, in this case, it's easier for me to think about adding k to both sides than it is to think about subtracting 5k from both sides. Both are equally valid choices. It doesn't really matter which one you do. I'm going to choose to add k to both sides. When I do that, negative k and positive k, well, they undo each other. That's 0. So I'm just left with 12 on the left. And on the right, I have 5k plus k. Well, that's 6k's in total, plus 15. Now I want to get k by itself. Reverse order of operations, once again, is going to help us get our way through. We'll subtract our 15 first because sadness, oh boy, sad mep, thank you. Subtraction addition comes before multiplication division in the reverse of PEMDAS. So in this case, 15 and negative 15 are going to undo each other. I'm left with 6k. 12 minus 15, that's negative 3. Last thing between me and freedom, I want to get k by itself. We'll divide both sides by 6 to accomplish that goal. Our 6's cancel out. We're left with k. And then I've got negative 3 over 6. Well, I could leave it like that, but what's a more correct version of negative 3 over 6? Well, it's a fraction, which means I've got to make sure it's fully simplified. Take 5 seconds. What's the simplified version of negative 3 over 6? 5, 4, 3, 2, 1, half. Good. So negative 3 over 6 is going to become negative 1 half. And there's my value of k. Fantastic. So we're done. This is everything that I wanted us to talk about today. If you are interested in doing a little bit more, let's preview what's coming up in class tomorrow. So we've talked about all of these different equations where variables are on both sides. The natural extension of that is, well, what if I bring in the same kinds of questions I was asking last time? In other words, what if I throw in an equation that not only has variables on both sides, but also contains fractions? Think strategically. What choice could I make to get rid of those fractions? That's the way we were thinking yesterday. What choice could I make here to get rid of all of those fractions while also accomplishing my goal of getting all of my variables to one side?